Welcome back, everybody. Spring 17, test 3. Short answer, first question. We're supposed to do a mechanism that accounts for the major product formed in each step. So we should know which one's the major product. Mechanism often leads us to the right product if we know our mechanisms. So we're going to attack which atom? Which atom's more positive towards the pi electrons? The H with an electronegativity of 2.1 or the boron with an electronegativity of 2.0. 2.0 is lower than 2.1. That's a more positive atom. Pi attacks the more positive atom. And boron would get a minus charge and a carbon would get a plus charge. Carbon says, no, I'm not going to be a cation when you have a minus charge and I'm more electronegative than you. Give me your H. So which carbon gets the H? The one that's a better carbocation. Which carbon's a better carbocation? The more substituted carbon. Which carbon's more substituted? The one with 0 carbons to the left or the one with a carbon here to the right? Well, carbon to the right means it's more substituted. Come back to the more substituted carbon. Make sure your arrow goes all the way to the carbon. Make sure this arrow ends at the B. Make sure this arrow ends at the carbon. Make sure this arrow starts at this pair of electrons. Make sure this arrow starts at this pair of electrons. Don't have it start on the end. There's an atom there. There's no electrons. Don't start in the middle. There's an atom. There's no electrons. Pi bond is a pair of electrons. An arrow is a pair of electrons. Both of these bonds happen at the same time. That is called Syn addition. That gets rid of 2 of our products that are anti-addition, the H on opposite side of the boron. The one with the more electronegative H is on the more substituted carbon is this one. We'll be explaining that in a second. And let's do the mechanism. Step 2 is the one that has 6 steps and then tautomerization. Steps 1 and 6 are both acid-base. So when you copy sodium hydroxide over to your exam page, just copy hydroxide. You don't have to cross off a spectator, just don't bring it. Please make sure you have an anion there. And it attacks the hydrogen in the hydrogen peroxide. That is reaction number 1, acid-base. I'm going to number them because I know 6 will also be acid-base. I'm putting my peroxide anion right underneath the boron there. I'm going to circle. What am I going to circle? I can save myself some drawing over here. So I don't have to draw the same group over and over. Everything up to, but not including the double bond, I'll call R. I'm going to attack what atom with the O minus? You're going to generate O minus several times. The first 2 times you attack boron with it in step 2. And then step 4. Step 2, you'll have boron. If you're tired of writing Saya, you can write R prime instead. There you go. R, let's not put it in blue though. R prime twice. B has a bond to the alkene and then baby blue R. And what else we got on there? We got an O. You're going to need the O bonded to O sigma bond because it's about to break. And how does it break? And how does boron get neutral? Remember, boron with 4 bonds is negative. Boron with 3 bonds is neutral. And we're alternating neutral, negative, neutral, negative, neutral in this sequence. We're going to go neutral next. 3. The carbon boron breaks and forms a stronger carbon-oxygen bond. That also gets rid of the lone pair repulsions between the oxygens by breaking that bond, generating hydroxide, which is an O-. Remember what you did to O- right above this one last time you made it, because you're going to do the same thing with this O-. And that B is still bonded to an O underneath. The B still has that bond to the O underneath. The O underneath is now bonded up to that carbon with a double bond. And the baby blue R group. Boron's back to 3 bonds for just a second. Hey, you made an O- here, you attack the B. You're making an O- here, you're attacking the B. The only way to get this reaction right is to spend the time. You know it's on the test. It's not a maybe. And now you've got 4 bonds to B again. You got your O double bond. Went monochromatic on there. Now we got our OH on top. It changed colors, sorry. And that was step 4. Put the other O on. Why? What was the purpose of doing? Put that O on so we could take the other O off. That was the reason we put the O on. We got to trade the O's off of the boron. Step 5, coming up to an acid-base step in 6. Remember, you're setting up for an acid-base step. You better have a proton ready with its bond showing. Here is the proton, O, sigma bonded to H. And what's the base it's going to react with? The base it's going to react with is the O- you just generated. And what's going to happen to the O- and H? They're going to do an acid-base step. Step 6. Acid-base, just like step 1. Base grabs H. Hey, isn't that going to make O- attached to boron attached to 2 Sias? Isn't that this thing right here? You want to show off? Here, have an arrow going to that too. And most importantly, you made this. H bonded to O, bonded to a alkene. You can keep your R. And the O is on the end. Get rid of the product where the O is not on the end. We'll explain why in a second. And what's this last 7th step called? We didn't have that in chapter 6. Step 7 was called Tautomerization. And the most important thing you got to know about tautomerization is it's got to be catalyzed. Second most important thing, a pi bond moves and a hydrogen atom. This is the hydrogen atom that needs to move. And there's the pi bond that moves to a carbonyl position. In this case, what's your catalyst? Well, what do we have over these arrows? Do we have a strong acid or a strong base? We have strong base. So that will be used. And its conjugate partner will also be used. What's the conjugate partner of hydroxide? It's water. And you made water way back when. I mean, you didn't need to show it, but you made it in the first step here. Doesn't this become water? Bases do what? Do they take protons or give up protons? Bases take protons. That proton there. What happens to the sigma? We alluded to this earlier today. Sigma becomes a pi, like that elimination reaction we learned. Except we're not getting rid of a halogen here. We're getting rid of a pi and protonating it. There's going to be a CH2 right next to the carbon that's an aldehyde, and that's true. CH2 used to be a CH next to the aldehyde. Now it's a CH2. Got the H from here. And that we got 13. We're almost halfway there. Circled our two products. We got 15. Got to explain my choice of major product. 2 points each. Ooh. Ooh. You got to explain the regioselectivity and stereoselectivity right here. And it all happened up here. We'll put a big explanation with a little telephone pole here. Pi attacks more electronegative, or less electronegative, sorry, more positive is what I wanted to say. Less electroneg boron, and H goes to more substituted carbon. Why? Because that's the one that spends more time as a cation. Why? Because of hyperconjugation. And you got to explain the stereoselectivity. That's regio. Regioselectivity. And stereo. Quite easily explained. Both new bonds at same time equals syn. That's why the H and the B are on the same side of the alkene. And we'll do another explanation of why the aldehyde and not the ketone. And that one has to do with the overall mechanism on the bottom. And we'll put, I don't know, put a double telephone pole. B gets replaced by O in mechanism. That's why it ends up on the end and not on the middle. And that's all I need for that. The overall result, there used to be a B on the end right here. And then by we got to this stage, there's an O on the end. Right here's where it happened. The carbon moved from here to be bonded to O here. That's where it happened right there. Here. That's where it happened. And it's label time. Label time. Why don't we do nucleophiles? What's synonymous with nucleophile? Lubnu. Lewis bases are nucleophiles. Why? Well, Lewis base is an electron donor, and it donates to it would have to donate to something positive, and those positives live in the nucleus. Makes sense. So the attacker is always the nucleophile. And here's it attacking the boron. It's a lubnu. And let's use something that sticks out a little better. Purple. This thing's getting attacked. And then the second arrow happens when they've become one molecule. So let's not describe the reaction based on this arrow. This is the one that got the game started. It's the attacker. So let's use our description based on that arrow. Don't do any descriptions when there's only one molecule involved. And when there's two, though, like here, we've got the Lubnu. The Lubnu is the attacker. And the thing being attacked is the Ela. And we'll save Bronsted till the end. If you're attacking H's and H is going from one molecule to the other, you start adding Bronsted stuff. Here we go. We got a Lubnu here. And the thing being attacked is an Ela. Loves electrons. Electron acceptor. Must love them or it wouldn't accept them. And then we have another Lubnu. And another Ela. And this has only one molecule involved, so please don't give descriptions. We got an attacker. And something get attacked. We got an attacker. Oh, this one's got it all. This one's got the attacking from the bottom. This thing's getting attacked on the H. And then it's turning around and being an attacker. Yeah, there's another molecule up there involved. And this thing's being attacked. It's a twofer with tautomerization. And then we'll do the Bronsted in pink. If you attacked an H, you're a Bronsted reaction. No, this H is actually attacking, but that was when it was one molecule. Let's see, what do we got here? Is it attacking an H here? No, it's attacking a B. Is this attacking this one molecule? Oh, we attacked an H there. Why don't we do 1, 2, 3, 4, 5, 6 in order so we don't miss anything? We're attacking a proton. You are a Bronsted base. Bronsted base. You're giving up a proton. You're a Bronsted acid. That's 1. Let's go to 2. Let's go to 2. Step 2, we're attacking and being attacked, but proton is not moving. So don't add any Bronsted. Rearrangements, we don't do labels. This is not attacking an H, so don't put a label. This is not giving up an H, don't give a label. One molecule, no labels. This is attacking an H. It's a base. Base that's getting attacked. Bronsted, sorry, an H. H that's getting attacked. A proton is what we call that, right? Bronsted. Here we are attacking a proton. That's a Bronsted base. Here, it's a proton being attacked. Here, it's a proton being attacked. And this is attacking. Got a lot of good stuff there. Wow, labels are a lot. I'd say there's more than 10 points of labels for sure. Yeah, it's a big question. All right, so that's a good start to our review. You guys are going to email me some review questions. Tonight, I'm going to send you the test layout based on old exams. I don't know if there's going to be a single exam that has what we need. We're covering less material on this one, and the material's shifted somewhat from normal semesters. So I may be picking and choosing from different tests. So I will leave you with that, and I will see you on Wednesday.
Professor?
Yes.
Can I just ask you a quick question in private?
I don't know how we'll do that. How about an email? I'm going to go straight to my email right now.
I actually already emailed you like a week ago, but I
Oh
don't know if
boy, I
you...
missed it. I get so many emails. I try and I miss some. But yeah, but I'm going to
I
go there
sent
right
you
now.
two emails.
Do you need to resend it or what? Just send me an email saying, look in your email if you want, and tell me what time and date it was, the old email. Could you do that?
Dr.
Okay,
Whitaker?
I'll do that.
Hello?
Yeah, I'm gonna email you too. I have a question.
Okay. I'm going
Thank
straight to
you.
my email. All right, guys.
Thank you.
Thank you.